Welcome to a lesson with Dr. Powell. Let's discuss what the derivative formula would be for the function if we have x to the n, where n is some constant. I mean, this could be considered like x to the fifth or x to the seventh. We're going to consider the case right now that n is a positive whole number, so a counting number. When we do this, we're just going to tackle this the normal way, where we take a limit as h for run goes to 0 of the function when we plug in x plus h, so just past, so we take the run forward from x minus f of x where we start all over the run h. So I want to picture h, and we start at the height f of x and we end at the height f of x plus h, because this is x and this is x plus h. So we compute this limit right here, and let's do that for x to the n. All right, so we do x plus h to the n minus x to the n all over h. Let's get a handle on what's happening here by looking at some examples and maybe seeing a pattern. First of all, notice that we're raising things to the nth power, x plus h. We can use Pascal's triangle to help us with that. For instance, if we want to raise x plus h squared, we end up getting x squared plus 2xh plus h squared. Notice the powers of x go down from 2 to 1 to x to the 0 even, if you want, like. And then powers of h go h squared, so 2, 1, and then h to the 0. Then notice that the coefficients, though, they're 1, 2, 1. They appear right here in this triangle, 1, 2, 1. Let's take this triangle and think about it for a minute. What if we did x plus h cubed? This actually can be seen by the next line on the triangle. This is how we get it. We take two adjacent spots, 1 and 2, and we add them. We get 3. 2 and 1, we add them. We get 3. And then we put 1s on the ends, and then that is the next line. That's the line of coefficients for x plus h, quantity cubed. So we end up getting 1, 3, 3, 1, where we have x cubed, x squared h, xh squared, and h cubed. Now, we can keep going, but in general, it might be instructive to realize that this whole bit right here, we can factor h out of. And then we get something like this. But it's nice to know that h is in there. Okay. You also notice, okay, so you can factor h out of that. Also realize that you have a plus x cubed over here. Now, when we're tackling this, notice if these were cubes, this part right here, we would take, goes in right here. X cubed would go right here. Now, so if we subtract x cubed from this, we have the h. Wonderful. All right, so the h is out. And that cancels with that h, so we're left with this. Then as h goes to 0, notice that that term goes to 0, that term goes to 0. Only one term is preserved. The first term in what we have factored, the part that we have when we factor out h, the first term there is the only one that survives. And that will be the derivative. So in other words, the derivative of x cubed is 3x squared. Let's use this idea and think about it for a minute. let's keep building Pascal's triangle and thinking how we can see what we're going to get generally. Okay. So let's go to the next line. 1, so adjacent, remember, to 4, adjacent to 6, adjacent add to 4, and then we put a 1 on the end. So when we take this is like x plus h quantity to the 4th, and we subtract off x to the 4th. So that first one's gone. Then we factor an h out of the rest. All these, after we factor out h, these still have an h with them, so they'll go to 0 and a limit, but this h will be canceled out. We'll only be left with that term. Now, what term is this? This is the next one down. From x to the 4th, we've moved down to x cubed. So we move down a power, and we put down the current power. So we have 4 times x cubed. In general, if we go down to the line where we have 1, n, and keep going, notice that we always have, see, this is line 4, and notice we have a 4 here. So on line n, for x to the n, we'll have an n right here. We'll get rid of that. The rest here, when we plug in h is 0 after we factor out, we'll just go to 0, and we'll be left with this term right here, which will be the term of x, n times x to the n minus 1, where we've gone down 1 power. So what we have is we have a nice formula for the derivative of x to the n. F prime of x is equal to n times x to the n minus 1. So in general, we can use this, and let's just look at a few different instances of this. If we had x to the 11th power for f of x, what would its derivative be? Its derivative would be 11, so we bring down the power. And then what's left up here is 1 less than the power, to the 10th power. Likewise, if we had f of x equaling x to the 7th, then f prime of x would be 7x to the 6th. Thanks for watching.